introduction, like for 2-3 minutes, and then I let you talking, Hubin.
Yes.
Sure. Let's start.
Perfect. So, good afternoon, everyone. Thank you for your waiting. Welcome to today's session on quantum computing for quantum chemistry. We will review UCC method and Adapt-VQE. Quantum computing has the potential to revolutionize quantum chemistry. Sorry, I forgot to put my camera. To revolutionize quantum chemistry by overcoming the scalability limitation of classical computing, particularly in simulating many-electron molecular systems. In this session, we will explore the latest advancement in variational quantum Eigen solver called VQE, including our open source package Open-VQE and innovative approach like fixed unitary coupled cluster, UCC, and the Adapt-VQE algorithm. Now, let me introduce to you Hubin. Hubin is currently doing his second year of master in quantum devices with the Université de Paris in partnership with École Polytechnique. This program focuses on high-level theoretical and experimental training with quantum devices and nanotechnologies. He has been working as an intern at the company Qubit Pharmaceutical for 6 months under the guidance of Dr. Mohammad Haidar, who will be joining later. His main interest is in quantum computing and quantum chemistry. He's also lead contributor in the open source package Open-VQE under the scope of quantum algorithm, scientific research, and documentation. Now I will let Hubin present his part.
Sorry, patience.
Okay.
Let me know, Nathan, if this is the way how it is, because
Yeah. Well, I can present to you. Take your time. I will just make a short presentation of you.
thank you. Yeah.
So our first speaker will be Dr. Mohammad Haidar, who is currently a senior researcher at Qubit Pharmaceutical, where he serves as a supervisor and mentor for master students. From 2021 to June 2023, he held a postdoctoral research position in quantum computing for quantum chemistry, certified by Sorbonne University, working with Total Energy and in collaboration with Atos quantum computing team. In 2021, Mohammad received his PhD in theoretical quantum physics from the laboratoire Kastler-Brossel, affiliated with Sorbonne University, ENS Physics Department, and Collège de France Paris. He earned a scholarship from Sorbonne University to support his doctoral studies. Prior to this, during 2016 to 2017, he completed his master's degree in high physics particle from Lebanese University and le laboratoire d'Annecy le Vieux in physical theory. And as for myself, I am a full-stack developer at a consulting company called Margot, and I'm undergoing a project of designing a drug design platform at Qubit Pharmaceutical. I hold a background in applied mathematics from Université Libre de Bruxelles and École Polytechnique. I am the administrator of the open source project Open-VQE, where I work on developing application and algorithm for quantum education. Now I will let Mohammad begin his presentation.
Yeah, thank you very much, Nathan. Hello, everyone. So do you see my screen, first of all? I shared it now. Is it clear or there is something to have been done before we start? Let me know,
it's fine.
Nathan.
We can see.
Excellent. Thank you a lot. So thank you, Nathan, for this introduction. I would like to thank very much Washington, D.C. and Toronto Quantum Computing Meetups for this organization, for this wonderful invitation. I'm very happy to have been speaking here with my my former internship student, Yubin Khan, who has been working with me 6 months, where he is going to speak about Open-VQE package in details, how to implement it, and how to make kind of use cases, how to implement the tools, and how to learn from quantum computing for quantum chemistry tools. So UCC methods and Adapt-VQE algorithms.
Mohammed?
Thank you again. I am now in New York, in fact, and it's pity because I would love to be in person in Washington, D.C. But I want to thank a lot Helen for all these organizations. Since few months, we have been trying to organize all together this event. And I want to thank the audiences for being there and for patience with us for 16 minutes in order to start. But I'm really sorry because there has been a problem on the Zoom of my account, but now it works. So Adapt-VQE and UCC methods are very important nowadays in quantum computing for quantum chemistry because quantum chemistry is an interesting and a promising application for quantum computing. When you work in quantum computing for quantum chemistry, you will be able to work with different applications like in drug discovery, like in electronic structure theory, in material science, in quantum battery, and whatever. In this session, I'm going to explain the review of the UCC, which is an important method in electronic structure theory, and Adapt-VQE, which is a version on top of the standard variational quantum eigensolver. Variational quantum eigensolver is a potential algorithm that is important to apply it in the NISQ intermediate scale quantum devices nowadays because they can be able to limit the number of qubits and the number of gates you wanted. So let's start. So we will start first with an overview of quantum computing and quantum chemistry. Then we are going to see what are the challenges nowadays and the computational requirements of quantum chemistry methods in the classical computers. Because nowadays, even you are having a HPC, large quantum computers, still the important quantum chemistry methods, which are advanced quantum chemistry methods, are really needed because they will bring precision and accuracy in the problem you are solving. And this is something we have to figure it out. So, of course, I agree that the classical computers nowadays they are pushing the boundaries in order to increase the memory stockage. However, we still think the quantum computer can do that in few days or even a few hours to do all the computations once a day. So I will go further for the motivation toward using the quantum computer in a quantum chemistry. I won't go to quantum finance and so on. I will let it for other speakers. And I'm going also to share a nice news today about an activity we have pushed at Hubin and me and other colleagues in the quantum education. We have done a very nice activity and we are going to show it for you in next slides. And I think it's very exciting for everyone to register and to apply for it. Then we are going to explain about the unitary coupled cluster method. So, you know, in classical chemistry methods, there is the coupled cluster method, which is a very promising method in order to work on the medium-sized molecules nowadays. And it's really bringing a lot of accuracy, as I said. However, as I said, quantum computer will be really important for implementing unitary coupled cluster. So I'm gonna go for the theoretical background, the significance in the quantum chemistry. Then I'm going to show you guys how to implement the unitary coupled cluster in the quantum computer and what are the methods that we can use in order to implement this method UCC. So then afterwards, I'm going to speak about the state of the art nowadays. Where are the researchers? What are the efforts they have been done since long time? What are the main challenges in terms of the number of qubits? What are the main challenges in terms of scalability with the gates? In terms of the circuit depth? So all these things have to be discussed in this session. Afterwards, I'm going to speak not so much, but a little about Adapt-VQE, because I know a lot of people are fascinated by Adapt-VQE, and it's very interesting algorithm because it's a new version of the standard VQE. And I'm gonna explain in detail how it works, the standard Adapt-VQE, how it improves on the top of the VQE, then how it's really efficient in terms of the improvement in the gate count and the qubit numbers, and what are the current main challenges. And then we will review the latest publications and where are the colleagues nowadays there and the researchers nowadays in the world in the advancement of Adapt-VQE algorithm. Then my colleague Hobin Tran is going to explain to us about the installation of OpenVQE package, how to use it, and what are the applications that the users like you guys can use it, and how can you learn from the tools of quantum computing for quantum chemistry. And then we are going to make a training tutorials with hands-on demonstration how to use it. So before we jump to the next slide, OpenVQE, it's a package open source, which I created with Total Energy, as Nathan said. And it is a really very interesting package because it has been published in Wiley, and it's really very well designed. And it's now growing further and further with my colleagues in the community. We are working on it nowadays. So whoever wants to join OpenVQE in the future, you are very welcome. So very briefly, who I am, as Nathan mentioned, I did my master in high energy particle physics in 2017 at the Lebanese University in Lebanon. And then afterwards, 3 years of a PhD in quantum physics at Laboratoire Kastler-Brossel in Paris for hydrogen molecular ion theory. And then a postdoc in quantum computing for quantum chemistry, where I created the OpenVQE package with Total Energy and Atos and Sorbonne University in academic. And nowadays, I'm holding a position as a senior researcher in quantum computing at Qubit Pharmaceutical Company. So my main achievements, I would love to just very quickly, I have been supervising 2 master degree students, Hubin Tran and Karim El Mahdi, in France, in Qubit Pharmaceutical since 6 months. And I have done a preprint article about using the Lie algebra structure with the quantum chemistry in order to work on the efficiency of the intercoupled cluster. During my postdoc, I have been creating the OpenVQE, and we published it in Wiley. And during my PhD, I have done 7 articles in quantum physics in collaboration with some people in journal Science. So here is the big surprise. I wanted to show it to you. In Miami, I have been invited last week, and I shared it to the fantastic colleagues there because they really wanted to work in quantum education. And this is an example of quantum education. What is this example? It's the Vietnam School of Artificial Intelligence and Quantum Computing, which I have been working in my free time with Hubin and the colleagues in order to create it. And this is a big example about the action in quantum education to let people learn about the introduction of quantum computing and artificial intelligence in Vietnam, in Hanoi, thanks to the founder of Tran Thanh Van, professor who invited us to work on that on ICISE Institute, who founded it there, and it's going to be in 17 and 23 up to 23 August 2025. So now we are currently increasing the efforts to secure the funding, and we are very happy that we are increasing the funding process to secure it. And we are happy to empower 40 students from over all the world in order to be there, which is really, you have just to visit this website there. And I will share it with Helen later in order to have registration there, and don't hesitate to contact me. And you can, of course, contact me through LinkedIn first, and then you can go to also the email also. We are really open to ideas and discussion from investors, educators about this. They are really welcome. And we are very happy to increase the bridge of talents gaps in terms of quantum education through this school, which is going to empower a lot of professors from Germany, France, and from the east of countries of western east of Vietnam. So now coming back to our main talk, which is quantum computing for quantum chemistry. That we need to make a lot of simulations. So in terms of chemistry, we are looking for accuracy. And for larger molecules like that, we need accuracy because this is very important to be applied for drug discovery and for material science, as I mentioned, molecular reactions, CO2 capture, molecular properties, and molecular docking through the process of drug discovery. But now I will focus on the method of electronic structure theory, how they are working in terms of quantum computing language. So motivation, applications in chemistry, quantum chemistry methods for solving electronic structured molecules and determining the electronic structure theory, the electronic energy, the molecular orbitals, the I mean, all these things have to be solved by advanced quantum chemistry methods like CISE or, sorry, like the CISD or the CCSD, the coupled cluster, or the, I would say the DFT methods or function. I mean, the FCI methods also are really important to solve that. But all these have limitations nowadays because of the computational cost and the memory and the time on the classical computer. So we need to speed up the computation, and it's really slow if you want to really reach a certain number of accuracy in terms of your energy. That's why we need to work on to see the capabilities of the quantum computing methods, the VQE, the UCC, the Adapt-VQE for performance these gains, because they are based on the superposition and the entanglement and interfaces between the bits, which is through the qubits used in the quantum computing. So I'm going to focus on solving problems in electronic structure theory through UCC and Adapt-VQE. So why classical computational speeds gains are slowing, and how and why? So as you have seen here in the curve, we have the accuracy, the vertical, and we have the horizontal, the computational cost, and can be the size of the molecule, the system you are going to solve. So you see, you use Hartree-Fock method, which is the simplest method, which is really not expensive, but it's not accurate, in fact. So we don't need it because, I mean, it's not useful. For perturbation theories like MP2 or configuration interaction double, CISD, or CCSDT, which is triple excitation on top of the double excitation, but using the perturbation theory, they can be used for medium size and molecular systems. And the problem is that in the classical computer, they need a lot of computation because, as you see, the CCSDT, for example, it needs n to the 7 of computation in order to perform the computation of these using this method. So how about adding quadruple excitation like CISDTQ, which is really more on top of triple excitation? You need quadruple excitation, and then you have to do a lot of linear combination of determinants up to quadruple. And this is something really needs 10 to the power 10, which is really going to be increasing further and further. But the main goal, the classical limits up to there, because for large molecules, FCI is not working, and it's only applicable for very small molecules. So to go further and read more about that, I will advise you to go to this reference downstairs in order to see how it really works and what is the limitation on the classical computer. So classical limit, and now we need to understand how we gain this FCI computation using the quantum computer. As all of you guys, audiences here knows the difference between bits and qubits. Bits can be either in 0 or 1 state. Qubits can be a leverage of existing the superposition states at 0 and 1 simultaneously. That's why we could see that the capability of qubits, that it can enable to process the quantum computation exponentially higher than the classical computer, and that's why it's something really could be very interesting for applying FCI and reaching FCI through the quantum computer. So to show how to reach the FCI in the quantum computer and why it's really problematic in the classical computer, just please guys look at this equation of the dimension of the Hilbert space is really related to the number of the orbital n0 and the number of the electron. So if you're going to increase the number of the electron and the number of the orbitals, let's say of benzene, for example, which is going to be 42 electrons, and you want to distribute them over 72 spin orbitals, then you need 72 qubits to do that. And this will be really high. This will be really large memory and time consuming on the classical computer. And we call it an exponential wall. The same thing for propane, you need to distribute 26 electron over 23 spatial orbital, and then you need 46 qubits in order to do that. So how about using the quantum computer? You just need 72 qubits, and you are going to apply all these 72 qubits, and you are reaching the FCI. So that's the main game and the play role nowadays. So here I also attach some references that could be useful to see the details, what are the resources needed, and this is the reference how to make the propane works. And people nowadays in the classical computers, they use 512 processes in order to compute 113.6 hours this exponential wall. So I do agree there is a competition now in the classical computer and the quantum computer for the future. So Where are we now? As I mentioned in the introduction, we are in the NISQ area. So as after Feynman 1981 about the simulation, there have been a lot of progress, a lot of significant progress in terms of investment by the government, by the institutes, by the academics in order to do calibration and in order to work. So nowadays the hardwares are in the NISQ era, and the quantum emulators are people who are going to, researchers, companies are going to produce emulators that could be really nice and efficient for students, for engineers, in order to mimic the algorithms and to play, to see the behavior of the certain algorithm you want to work in. So I would advise also to read this article, which is going to be Beyond the Buzz, which is strategic path for enabling useful NISQ application by Pratibha, by these guys, I mean. And this is very interesting because people now, they are trying to combine AI and the quantum together in order to see what could be the capabilities of AI to work on the NISQ era. And this would be really interesting to read this article, which has been published, which has been out since few months by the interesting colleagues. So, okay, after NISQ devices, as all of you may hear, that we need a quantum advantage. Quantum advantage and quantum dominance are related. It's the way where the quantum computer is really dominating the classical computer, and you will never see the advantage of the classical computer in front of the quantum computer. And that's why we need certain application, as I mentioned, as you see here, CO2 capture, drug discovery, etc. And we need at the same time to work on the quantum error correction methods and how it will be applied in 5 to top 10 to the k qubits up to 2028. And then afterwards, we are allowed to go to the fault-tolerant quantum computing, where up to 2030, we don't know which year will be, but will be very exciting to see millions of qubits on the quantum hardware. So who are the companies leading the quantum computing nowadays? Okay, we have Europe, America, Asia. In Europe, I would say I would start with IQM, Pascal, AQT, Candela, C12, Alice and Bob, etc. Of course, we have many also in France and in Europe. America is also IBM Quantum, Google Quantum AI, Rigidity Quantum Computing. As you have heard also that Google has recently released some blogs about the Willow, which is really interesting for its next generation quantum processor for the scalability of the quantum error correction, and they use the surface code method. And this is really a huge key milestone what Google AI have done, and this is really interesting topic I have discussed in Miami last 2 days, and we are really interesting to go further and see what they are doing. And in Asia also there's Alibaba Quantum Lab, Baidu Quantum, and TT Quantum. So all these companies are very, very working very hard and putting a lot of efforts in order to let the quantum computing and the quantum advancing existing in the next few years. But okay, we have quantum computer hardware. Now let's move to the software companies also, because also they are trying to offer the best classical emulators that could be useful for the future and nowadays. So I will start with Evident Captiva. I love very much the work in Evident because they have provide me the possibilities in order to work on OpenVQE package, and through that I created the package through the tools because they are really very well designed, very well clear, and that's why my students also have been love it so much, and we are really going to continue with it. And not only because we have also NVIDIA CUDA, we are trying also to integrate tools from NVIDIA, which are providing a lot of acceleration nowadays. And Microsoft also, they are offering cutting edge simulator technology integrated with the Azure Quantum. So how it's fascinating if we are able to make OpenVQE package integrating all these tools, not only Evident, but also NVIDIA tools and Microsoft. And this is what we are going to do in the future. So NISQ limitations, as I said, two main resources, the number of qubits and the quantum gates. As you see here on the right, we have different words, we have different structure, we have different things. So I would start from the extreme left. I have 0, 1, 2, as almost of you know, these are the 3 qubits, started the registration of the circuit. Then I apply 3 Hadamard gates. Then I would have an output like a superposition of states. And then I applied Control Z gates. And afterwards, I have another cycle, which is Control Z gate between the first and the third qubit. And then in the fourth stage, I have 2 Hadamard in the second and the third qubit. And then I do the measurements in the circuit. And this is just, I want to show how it will really work nowadays in the UCC methods and Adapt-VQE. This is the way how to make an analogy for the people who are really not familiar with that, just to give a picture and a whole image about this. So for people who are interested to see how they work and how they fail the NISQ and how to test them, I really would recommend to go to this paper because they explain in detail this session in detail, and I really love it. So whoever wanted to exchange and to interact with me about this topic, I will be really very happy. So variational quantum eigensolver, as I said, it is a potential algorithm to apply it in the NISQ devices. It has been already successfully executed experimentally on the real NISQ devices, and NISQ devices, there are many like super quantum computer, so superconducting, photonic and trapped ions, or atomic also. So here are the people who are interested to see more why we are mentioning they are successfully applied on a certain number of qubits, few number of qubits. You can please read these 3 websites, and they are really explaining in detail how it works, the experiments. So I also would suggest, in order for people who wants to learn more about VQE, who really would love to learn more about it, how it works, I would advise to go to the left for the Variational Quantum Eigen a review of the method and the best practices by Jules Tilly and others. Also, myself and my colleagues, we have also published an articles in Wiley, and this is what we are going to discuss today about it. And it's really explaining not only the VQE, but also the UCC in a nutshell and the tools, because it's very interesting to see an article which really makes the bridge of the gap between the hardware, between the tools, and between the methodology by itself. And that's why we try to make it understandable for people, and we are so happy to make it. So now, how is VQE applied in quantum chemistry, and what is working? What is its working principle? This is very important to let you know how it works. So variational principle, as almost physicists here, they know that it states that the energy, let's say the energy W, of the approximate wave function is always higher or equal to the lowest energy. Once we arrive to the exact solution, we are really getting our exact ground state. But I would say in variational principle, you wouldn't arrive to your exact energy, you would arrive to the higher energy or equal to the lowest energy. And this is what we call it the approximate ground state. So how the VQE works. As you see here, we can start with 2 steps, 2 things. We have it's hybrid. It's using the quantum processor unit, QPU, and it uses the classical computer, which is the main role of the optimizer. So up is the QPU and down is the optimizer. We have different optimizers nowadays. We have Copila, CG, PVGS. So you just need to go to the SciPy library, and you can check what optimizers you need. And there are a lot of also progress in the people who are trying to also work on efficient and clever optimizers. And this would be also very nice for making a very fast and very quick VQE algorithm. So let's see how it works. So first of all, we need to prepare the state, whatever UCC, hardware efficient, and whatever. So I applied it into the Psi Hartifuck, which is my reference state, because in chemistry, our reference state is Hartifuck. And the quantum computer will prepare it, and it will also compute the energies and sum the series of the energies until you get the E theta, which is the total energy of the total subterms, which you are going to decompose your Hamiltonian. Then each Hamiltonian species will be summed until we call them the weight summation, and then you get your total energy. However, the optimizer uses the measured energy in order to update the parameters iteratively. And that's what you are seeing, theta n plus 1. When you update it from the optimizer, then you feed it back into your circuit, and then you get your energy. And then afterwards, the optimizer, it will go further and further until you get your minimum energy, which is the E theta star, and this is the final energy. So this is the standard VQE, how it works for people who are really not familiar about VQE. So in VQE also we have restrictions because we're applying it in chemistry. So we are using Born-Oppenheimer approximation. So Born-Oppenheimer approximation, it's, I think, almost all of you here, physicists, works on that. But people who are not familiar, let me explain it to you, and I would be happy to explain it in detail. So in the right figure, we have A and B, big letters, and I have I and J. So A and B are the largest components or the nucleus inside my molecule, and I and J are my electrons. So how to map that into an electronic structure Hamiltonian as you have seen, there are a lot of terms, one in blues and the others are not in blues. So those in blues are really related to the electronic contribution, which are really those we wanted to solve, because the others we want to ignore them because we don't need the velocity of the nucleus. That's why we fixed it and we ignore it, and we just put the interaction between the nucleus and the other terms, which is the kinetic energy of the electrons, the potential energies, and the electron-electron interaction terms, and the nucleus-nucleus interaction terms. So I'm sorry, we have to put that in blue also, but we missed it. So in quantum chemistry, we need to think about how to map these equations into second quantization formalism or first quantization formalism. But now I want to show also second quantization only, because for people who are interested to think about first quantization is really very interesting. You just need to contact me and we can work together on that, and I would be really happy. So let's now focus on the second quantization. In the second quantization, you have several properties. This is the way how your Hamiltonian is really a series of annihilation and decretion operators. HPQ is the one electron and HPQRS is the two electron system. And here is the way how you need to map the fermionic system into qubit spin systems. That's why because we need to measure them in the quantum circuit, as I mentioned in the last slide. Therefore, I should have a Hamiltonian from fermionic into Hamiltonian. We call it spin Hamiltonian because it's summation of Pauli terms that we really need to measure. And this is the way how the variational principle works, as we mentioned. And at the end of the day, we sum all these Paulis. I'm sure we are going to get plus or minus one, but then we have also the alpha j's, which are the coefficients we need to put them because they are coming from the HPQ and HPQRS. So now we finished from the Hamiltonian. Let's move now to the unitary coupled cluster. In unitary coupled cluster, as you see in the top equation, we have an exponential of t minus t dagger that makes it unitary, in fact. So the addition of the Hermitian conjugate operator on top of the t, it is the making it unitary. We need it unitary because we are applying all this in the unitary gates. So psi HF is our Hartree-Fock state. And now what are these T minus T dagger? As you have seen in the equation, they are single excitations and the double excitations. They are moving from the occupied to the virtual states. As you have seen, we can have single, we can have double, we can have triple, and we can have quadruple. So now we are going to focus from single to quadruple excitation in our session, because I have prepared for you guys how to you see the efficiency of adding triple and quadruple excitation and what are the drawbacks when we are going to add them and implement them in the quantum computer. Remember one thing, if I have an exponential of t minus t dagger, I'm going to have exponential of summation. That's why Trotter approximation is a very smart way how to broke the summation of exponential, no, to broke the exponential summation into exponential product, and that's why we call it single step. But there are also first order, second order, third order Trotter approximation you can use in your work in order to see how can you increase the level of accuracy in your wave function. So this is the workflow of quantum chemistry. So we have top panel and we have bottom panel. And QLAM is the quantum learning machine from Atos. I have just to tell you that how it works. So on the top panel, you can just initiate your quantum chemistry method you want. For example, you can start to say what basis set you want, the geometry you want. Suppose I have 4 hydrogen, 6 hydrogen, then I have to say I need 6 hydrogen. I need to see what is the bound length. The Hartree-Fock states also, the HPQ, HPQRS, which a lot of people nowadays working in the optimization of this because it's very important to work on that. But this is another topic to discuss. But this is something also very interesting to see that the way how we are also making the tools are very nice, because they are making like an open fermion, for example, package or PyOSCF. We're trying to make them an Open-VQE very well documented, and this is very nice. So as I explained, we have fermionic to qubits. I have Hamiltonian. Suppose sometimes I have active space selection because I wanted to work only on a special dominant orbitals, and I want to ignore the others like occupied or non-active. So I would have a tool that could explain this in very well detail. Also representation, Jordan-Wigner, parity cave, parity, these are ways how to map from fermionic to qubit. Ansatz construction, how to map it into circuit. I will show you in the next slide how to do that. And then how to measure the Hamiltonian. So this is the circuit, and this is the Hamiltonian as a series of Pauli terms. So once I have that, I'm gonna have a kind of job which is going to stack my ansatz and the Hamiltonian, and then I need to just say how many number of shots I want to shot on my circuits in order to see the measurements. So some people, they are clever, they like to go to sophisticated plugins, we call them sophisticated jobs. So they don't just want to work on the standard VQE, they wanted to go to different categories, different versions. So you can use connectivity, get base, qubit ordering, depth optimization, etc. You can also try to work on jobs that can also grouping of Pauli terms, because I have seen an article recently, they are trying to group some, to make partitioning of the Hamiltonian at the end in order to cleverly let the circuit, many circuits make parallelization of the computation of the operators. So this is how in the QLM library, they delivered all these plugins. And in terms of QPU, you could have perfect simulation, MPS, matrix per state, Schrödinger, stabilizer. Even if you want also to work with noisy simulation, and then you can interface to the true QPU. Once you have it, you can stack your job on top of that very immediately in one code line, and then you can switch from IBQM to Google to Rigidity, sorry, IBMQ to Google to Rigidity, and so on. So in terms of people who would like to see QLM, you just need to visit Evident. They are really making a nice work. I really want to congratulate them. I'm following them. They have Captiva 800, and it's really specialized in classical and quantum simulation performance. And that's why I would advise you to see the PDF there. It's online, so you can read how it works and how much qubit if you can simulate in your laptop, how much qubit you can simulate in the machine, how can you access the machine, and so on. So now let's go back to the science more and to the electron correlation types. So as I have mentioned, Hartree-Fock wave functions, you don't have electron correlation, and therefore it won't be precise, it won't be really accurate, so it won't be useful for what we want. So we need methods that can really play with and we can work with electron correlation. So as some chemists knows that we have post-Hartree-Fock methods, like we have CISD, we have also coupled cluster, and we have coupled cluster, we have MP2, and so on, and many others. But I wanted to focus on two types of correlation we have to take care about. So when I say dynamic correlation, is the way how you are working in short range electrons, like in helium atom, the error correction you are doing from the exact to the Hartree-Fock, it's really captured by using a single reference method. So you don't need multi-reference methods in order to capture the electron correlation. However, in static correlation, when you have really stretched bounds like in H2, you need to add the error correction from the correlation, but you need to capture it. So you won't be able to capture it from a single reference. You need multi-reference methods in order to cover this static correlation. Of course, because it's really have a lot of applications I want to show you in the next slides about multi-reference and the single reference. But I will not focus on the multi-reference. I will go further into single reference, but nevertheless, I'm going to show you what are the methods that can be used in the multi-reference states, and what also the quantum computing methods in the multi-reference state can be useful for the future. So for the single reference methods, as I mentioned here, we just have CCSDT, DLPNO, because these are ways how to make enhancement in the computation plus accuracy. So these are classical methods. Quantum computing methods, unitary coupled cluster. I didn't say that there are more, because this is the only common method now in VQE that can be used on top of single reference method. And this is our main focus. In the multi-reference methods, we have KSSCF, we have the MCSCF, we have the restrictive active space SCF, we have the CAS PT2, and we have MRCI and MRCC. So let's say for MRCI and MRCC, these are multi-reference coupled cluster or configuration interaction. CAS PT2, it's adding the static correlation from the CAS case, and the PT2 is from the MP2 method that can add both of them because it will cover the dynamic and the other will cover the static. Then you can kind of combine them. Restrictive, it's kind of to divide more and more the active space. So you don't want all the active spaces. So you just need that. DMRG also very interesting because it will be also able to cover dynamic and static correlations for a strongly correlated system. And KSSCF, as most of you know, that it really has a lot of advantage also, but at the same time, it will not give a lot of accuracy because we are really missing a lot of exact terms. That's why we need the RSSCF because it will be giving more and more localization. So in terms of quantum computing methods, there are many. I would say there is this very interesting article, multi-reference intercoupled cluster. I really love it, and we are going to come back to it in the last slide of the session. And also they explain the way how to, they explain the way how to use the multi-reference state. We don't need Hartree-Fock. They explain the way how the algorithm really works. And this is really advantageous for really strongly correlated systems who are really needed the multi-reference states. Generalized intercoupled cluster also in this reference, I attached it here. It's really very important because in generalized, you are able to generalize all your excitation. You don't need only single to occupied to unoccupied like we are doing in the double excitation, UCC. CAPS, UCC, GSD also, it's a kind of how to excite you the pair of excitations using the generalization also of single and double. LAS, it's a localized active space selection USCC SDT, which is as it's selective CC SDT of single and double. And I love this article very much with my colleague. I know him very well, Metra, and he really presented very well the last USCC SDT, how it works, and in a very nice detail with particular molecules like betadine and so on, how it works, this method. This is very interesting for industries also. So I would really advise to read these papers, and I would love in the future to work on that also because it's very interesting. So now, as I said, we are focusing on UCC families and single reference and how to apply them in NISQ devices. So as I said, UCC, it's a kind of, it's a variational state preparing my evolution of the summation of fermionic terms on top of the reference states, which is the initial Hartree-Fock. Properties like it's chemically inspired, applied to NISQ, very good accuracy, and it will really have fewer parameters than the non-chemical ansatz like the hardware efficient ansatz. However, I would have a lot of high number of CNOTs, and CNOTs are really the main source of noise nowadays in the NISQ devices because they are making entanglement with two qubits and they are needed in the UCC. So I will show in the next slide how to map UCC into circuit, and you will see that we need a lot of CNOTs. And this is why we need to reduce the number of CNOTs. This is why we need more and more intelligent methods, more and more intelligent and efficient algorithms that could be helpful in order to keep the chemical accuracy, but at the same time reducing the number of CNOTs. For an advice for people who wanted to learn about the versions of UCC, I would really recommend to go to an publication, and they really make an overview about the intercoupled cluster methods, and I love it. From this article, I learned a lot of things, and for people who are passionate about intercoupled cluster, you just need to go there and you explain in detail the things. On the right, you see we have single double excitations, so single and double, and then for beryllium hydride, you see here we have T1, T2, T3. I have single, double, triple, and I need to preserve the symmetry. So I need to preserve the number of particles, the total spin, the spatial orbital symmetry. All these things, we can see them in the next slides. So symmetry is very important, key in the way how to reduce the number of parameters. And that's why I used it when I applied triple excitation, and we published it in an article, physical chemistry A, sorry. And we have tried to get a lot of accuracy, but at the same time, we used the point group symmetry on top of the particle and total spin symmetry. So as I said, in order to implement it on this device, we have to use Jordan-Wigner, we have to use CNOT staircase method. I do agree there are also very smart and efficient now fermionic circuits that also map the exponential into circuits, but they are still also have a lot of CNOTs. So we need more and more clever ways how to reduce the CNOTs further in order to make it more efficient and compact. If I use CNOT staircase method, each single excitation will give me 4 CNOTs, and each double will give me 16 CNOTs. Why? Because if I have a single excitation and I map it, I will have XY, and then this XY will give me 4 CNOTs. If you go further into CNOT square method, you will learn more about it. Also, double excitation, you'll have 16, because if you map your double excitation, you get 8 terms in Pauli's, and then you have to multiply them by 2 because you are doing the Hermitian conjugate with it, and then you are ending up with 16. But for example, here, if you see, we have an operator of Z0, Z1, Z2, Z3. I have 4 qubits. Then I have 3 by 3. I have 6 CNOTs I need, because it's really the way how to map the exponential of theta of Z0, Z1, Z2, Z3 into this circuit. And RZ is the rotational gate that is really parameterized with the number of theta. And imagine you have a lot, then you have a long circuit, and that's why the main problem nowadays is the circuit depth in the intercoupled cluster method. So, chemical accuracy and strongly correlated system. How about going beyond the double excitations? Let's move to triple. Let's move to quadruple. But as I said, we need to figure out a few things. So, as I said, we have extension of the tritorized coupled cluster to triple excitation. I have published it, I think, in April 2023. And quadruple excitation, very cleverly, Fedorov and his colleague also, they have published an article about unitary selective coupled clusters. So they select the most important excitation from single, double, triple, and the quadruple. In a more efficient way, they use the pre-screening methods in order to select these fermionic excitations. In my case, I use the symmetry, point group symmetry, and the spin symmetry and others in order to reduce the number of parameters. But I stopped at triple excitation. As you can see on the right, 2 figures, one at the top, one at the bottom, both of them for beryllium hydride molecules. You need 14 qubits because you have 14 spin orbitals. It's really under the D2H point group. So in the top, we compare the double excitation and the triple excitation, and you see on the curve, for all the bound lengths, you have really at least more than one order of magnitude of improvement in terms of the chemical accuracy. Down, in terms of unitary selective coupled cluster, they have tested it in 3 bound lengths: 1.3, 2.6, 3.9, and you can see here I didn't put here the horizontal part, but this is the number of the parameters you are consuming in your ansatz, and here is the chemical accuracy, the error of your exact energy with respect to the Hartree-Fock state. And as you see, in the selective way, it's a kind of dynamic and iterative, I would say, that you can add the parameters, then you can optimize. Then iteratively, you add more parameters and you optimize until you get your chemical accuracy. Again, this I think is not in the this is in milli-Hartree. So I am sorry, I have to add the unit there, but I mean, at the end of the day, you would reach 10 to the minus 5 because of Hartree, because you have to see that it really gives a lot of accuracy, but at the same time, they reduce a lot the number of parameters. You see here the double excitation, they have limitation. So these are important because if you have a large system like more than BH2, then you need to use the UCC or whatever, so you need accuracy. But that's why you need also efficient method like symmetry and pre-screening methods. Okay, I want to stay in my fermionic type excitations, but the problem in these methods, I have triple and quadruple, which they still need a lot of number of CNOTs. Even with CNOT staircase method or with efficient methods, I still need a lot of number of CNOTs. So there are clever people from India. I want to say hello to them, really. They did a lot of compression. So they didn't use high rank excitations. They play the role and they really make a big achievement. For my colleague and his colleagues, Raoul Metra, so he did a nice article about noise-independent route toward the genesis of a compact ansatz for molecular energetics, a dynamic approach. So they these nice colleagues, they did a nice way how they create a dynamic ansatz that is really based on a threshold that you can tune the way how you want much chemical accuracy, at the same time how much you want number of parameters in your ansatz. So at the same time, their method, it doesn't need triple and quadruple excitation, and they reach almost the same chemical accuracy. So this is the way how I would love the advancement on top of triple and quadruple. They move to double excitation and the single excitation. At the same time, they efficiently reduce the number of parameters. But again, they also have large number of C-nodes, and I think they will work on that in the future. So maintaining chemical accuracy, okay, but how to minimize the number of C-nodes in a fixed ansatz? I want to remind you again, guys. So when I say fixed ansatz, for me, it's like I don't need to use any dynamic ansatz. I don't need to use any pre-circuit measurement ansatz. I want just to have my ansatz and I just stack it directly on the quantum computer, on the QPUs. So there should be a way how to figure out this ansatz. So needs a lot of work. And this is what I have done with my colleagues at Qubit Pharmaceutical. We have working on we have working in a way how to keep the fixed ansatz, and we reduce a lot the number of of operators and the CNOT gates. To see that, let's see in the next slides. So we try to make the title as non-iterative disentangled unitary coupled cluster based on Lie algebra structure. Because first, I don't want to see the iterative methods there. Disentangled is a new version of coupled cluster because it's an exponential product without rotorization. But Lie algebra is very important because it helps you to skip out the ordering problem. So if you are able to use the Lie algebra, you are able to commute your operators and you don't need to have problem in ordering. So even if they are anti-commuting, they are bringing you another operator, but this operator will stay in your pool. But the way how to make it scalable, we really find a way how to make it linear based on some references. And then we tried it to make it efficient by combining symmetry. So we work in the qubit. So we never work in the fermionic because fermionic will give me a lot of C-nodes. So cleverly, if you work in qubit plus symmetry plus Lie algebra, you are going to have a nice impact. And this is what we did. So as you have seen here, on the top, we have robust minimal complete pool. So it's a nice way how to make a starters of my pool of Pauli terms. I don't need any more fermionic, but I need to be careful because we need to find very strong correlation operators on top of my Hartree-Fock state. That's why I call it robust, because you can create a minimal complete basis using Lie algebra, but you need to make it robust. So you need to figure out how to link back to your fermionic excitation, but you enforce the symmetry. This is what I did. And I did all these things, parity, point group, in terms of how to create symmetric starters. The algebra, it will help me to work on T1 minus 2 operators. So this is another discussion, could be in the future, how to, for people who are interested, how to work on that. So I would be happy to make a presentation in the future, how to use the Lie algebra, but it's not our focus there. So NIDAC, it's the method which I call it non-iterative disentangled unitary coupled cluster. As you have seen, you have product of exponential, but you will have a lot of nice way because everything is only 2n minus 2. So you make it very well compact, and this is the way we need. So in the 3 and the 4, in the 3, you see the result of BH2. So as you have seen the curve there, the best one is the one of strong symmetry plus using the MCP. It really show no barren plateau problem. It really show no false local minimum. It's really amazing. You have no flat problems. You have no false minimum. However, if you only weak symmetry in your operators, then your disentangled unitary coupled cluster will go to a local minima false. Or if you want to also to make weak symmetry plus MCP, even though you want to improve better, also again you falls. But then if you put all this together, again, symmetry, unitary coupled cluster, and robustness of my excitations, then I'm gonna go to the true local minima, and it's really very fast convergence. And that's the main impact of Lie algebra structure there. So I have a fast convergence with a fewer number of function evaluation. Function evaluation is just the number of optimization steps I need in my optimizer in order to arrive to a local minima. So I need only 800 in my problem of 6 hydrogens in order to arrive to 10 to the minus 12 precision. However, in beryllium hydride, I need between 750 to 1000. I don't exactly remember the number, but it will also get almost the same precision. So that's why, I mean, it really comes to be applicable on many systems. However, we have to be careful about something. I will explain it in the next slide. I just want to focus on this one now. So maybe some of you are really chemists and they really want to see what is the performance of an IDAC with respect to the other fixed ansatz. So beryllium hydride, this is just on the left, the dissociation energy curve. And you see on the right, the most important thing is, again, is the error with respect to the Hartree-Fock. Ignore USCCD or UCCSD, which only is double excitation, and we know that double excitation will not be enough, so we need triple, quadruple, and so on. So based on the Fedorov work, I have launched a program of USCCSDTQ, and I applied it. And you see here on the golden one, I mean, they just arrived to 10 to the minus 6. However, in non-IDAC, we have really big improvement, about 6 orders of magnitudes, and especially in the equilibrium part. And that's why I would say NIDAC is really efficient method in terms of really high precision chemical accuracy that overcomes the quadruple and the triple excitations. However, we need to focus on something also. NIDAC is only, of course, it can work on 2n minus 2 pool of operators, but the way how to compute the Lie algebra on the classical computer is really high. So the cost is high. That's why now I would love to see improvement on that in the future. So far about what we have written in the article there, we have written about 20 qubits. But of course, we need to skip out the scalability problem, and this would really need more and more further works in the Lie algebra in order to make it not a problem of scalability. Once we do that, NIDAC will have a big win. So now about Adapt-VQE approach. I'm gonna finish soon. So Adapt-VQE approach, it's different from the standard VQE as explained, but it is how to construct my ansatz adaptively using the gradient measurements of the operators from the pool. Once I create this ansatz, it's gonna be very compact in terms of number of parameters and number of CNOTs. How to see that? So as I said, 2-qubit gates are the main problem. So because they have often an order of magnitude higher than the single qubit counterpart. Google, I mean, they have published that in 2021, and they said that in the quantum computer datasheet, minimizing the CNOT is really crucial for experimental success. So Adapt-VQE, that's why in chemistry problem is really promising. And the only way that constructing an infinite number of 1 and 2 body operators using the gradient measurements. Gradient measurements are just you have to compute your commuter of the Hamiltonian with the operator you are really fascinated with or you are interested with, and then you compute the gradient measurements to see how it really deviates with respect to the Hartree-Fock state, and then you can say if it's really high, then you add it. If it's not high, then you don't add it. So nowadays, a lot of people, they are doing kind of novel approaches how to play with the pool, because having a novel pool is very important because it can help you how to construct a very compact wave function. So that's why it's really very well designed, Adapt-VQE better and more than UCC-SD. And I don't want to compare here with UCC-SDTQ or UCC-SDT or with NIDAC because it really needs a huge concentration on that part because we have carefully to see what are the resources we are using in order to compare different methods. So here are not fixed ansatz, these are adaptive ansatz. I would say they are dynamic, they are using pre-circuit measurements, and that's the main bottleneck of the Adapt-VQE because of the high cost of the gradient measurements you need. So you need a quadratic scale, which is n to the 4. So if you have four operators in your pool, then you have a lot of operators to measure. You have to measure them, and then you have to also add the Hamiltonian also in your the cost of your Hamiltonian, because you have Hamiltonian and the operator. Then you need n to the power 8. But as I remind, there are also people working on the reduction of the number of measurements in the gradients and the cost. So far they arrived to the linear scale 2n minus 2, but again, it needs a lot of iterations in order to arrive to the chemical accuracy I wanted, and that's why I wrote here many iterations. So how it works, Adapt-VQE, you see here. So thanks to my colleague Hubin, he tried to help me on making this beautiful schematic of Adapt-VQE. So here I have on the top left, I have iterations. So because it's Adapt-VQE, we have to start to think that there are a lot of iterations. So how to prepare my state? So first of all, I start with the Hartree-Fock state, and then I need to measure all the operators. I have them in the pool in order to compute the gradients. So if I have 100 operators, then the quantum computer have to measure 100 gradients, measurements, in order to get the largest gradient in order to select this operator. So we sum all these gradients at this iteration k equal 1, and then we see if they are less or equal to a certain threshold. If they are less than this threshold, then we have to use them. And then we have to put them as the largest gradient. And then we have to expand the ansatz, adding these important operators who has these largest gradients on the top of Hartree-Fock state. So then we optimize all these operators have been added newly, and then we have to continue to measure again the next iteration, again, all the operators in the pool in order to get all the gradients from the previous state. And then I will really need to validate the threshold again, and then choose again the largest operators with respect to the previous iteration. And that's why we have to add this new operator theta k and to optimize everything there in order to go back and forth until I skip the convergence criterion problem, and then I will end my Adapt-VQE and I will have my compact ansatz. However, as I mentioned, there have problems here, not only of the gradient measurement cost, but here sometimes you need a lot of parameters. So compression of the parameters is important, and the way how you initiate your state is very important. That's why there are a lot of colleagues recently have been working on this problem, and I will mention who are they next slides, and a lot of people working in the novel creation of pool that can be done. We call it CAO, which is something called couple operator exchange pool that can be really helpful. And of course, there are people who have been working also how to choose operators once a time, not only one and add it, and then one and add it, then one and add it. So this is something could be really needing a lot of optimization steps and function evaluations to complete my answers. Therefore, there are a lot of versions of Adapt-VQE on top of the standard one. So the people who are interested to see, that's why I said I love this article, which is about the multi-reference unitary coupled cluster. As you have seen, their work is there, and this is their article. They showed at a given accuracy 10 to the minus 5 Hartree test on LIH, H6, and BH2, and they compare different fixed ansatzes and Adapt-VQE ansatzes that have been simulated in different references. Here on the right, you can see all the references related. I'm sorry I didn't put the 39, but I think you can find it in this reference. And as you have seen that a lot of play game in order to find the best and most efficient Adapt-VQE algorithm in order to say that this is the lowest CNOTs I have, or the lowest, lowest parameters, but it's not written here the number of parameters, so it should be written also. So, okay, here we can say that the Adapt-VQE also can be something competitive with the multi-reference UCC SDT also, not only for single reference UCST, because it really can be covered for both, and that's the main advantage of Adapt-VQE also. And so, yeah, I mean, this is the way how you see that people, they are trying to reduce the number of CNOTs as much as they can. So for interest, I would say you have to some kind of algorithms that have been published so far. There is Tetris. I love it. It's kind of iteratively how you build your ansatz by few operators once at a time in a way dictated by the problem being simulated. So they have done a lot of simulation using hydrogen molecules, beryllium hydride. Also, overlap Adapt-VQE. It's really very much interesting algorithm. And because I mean, in this algorithm, they kind of um, developed an ansatz important for strongly correlated system, introduce the overlap Adapt-VQE to build their wave function by maximizing their overlap with any intermediate target wave function that already captures some correlation, electron correlation properties. And that's why they also arrived to a very nice and compact ansatz with respect to the number of qubits. Also, a key recommendation. There are 3 articles there. This is one has been in July 2024. They reduced the resources required by Adapt-VQE. They use the CEO, as I mentioned, the coupled exchange operator, and they improved the subroutine by these fascinating colleagues, and they have done it. So it's very nice to read it, to see the state of the art. Also, Giata Traori and colleagues, also they have done the shortcut to chemically accurate quantum computing via density based basis set correction. So in this article, they really are, I think, arrived to 32 qubits using Hyperion simulator as written in their article. So this is very fascinating. And also vibrational Adapt-VQE, critical points to problematic conversions. So vibrational, I would say, I'm sorry, I have not to write it here, but I mean, when you say vibrational, it's different from electronic structure because they add also the vibrational properties using this Adapt-VQE algorithm. So now I wanted to move on to the Open-VQE package. Yubin Tran will go on to explain how to use it and how to work on it. But before we start, Yubin, just let me add a few words about Adapt-VQE. So Adapt-VQE algorithm, Open-VQE. Open-VQE, it's published an open source variational quantum eigensolver extension of the quantum learning machine for quantum chemistry. So the credibility of this package is amazing because we have also compared that with many references at the end of the table of this article, with Microsoft, with Google, with Spinalen, I guess. So I think with a lot of packages. So since then I created this package. I have tried to see how it should be also applicable in different countries. So I have now 35 contributors from different countries in Europe, Asia, and USA, and they are really doing a lot of nice contribution as an open source nonprofit. They are really amazing, and I want to congratulate all of them. And I'm sure they are here on the presentation. I want to say to all of them hello, and you are really amazing because you are growing Open-VQE with me. Nathan also, the moderator, is amazing because he's kind of working very largely on the package now, and he's really fascinated by Open-VQE, and he wants to make whatever open source helpful for students and engineers, applicable and accessible would be great. So I would believe the tools of Open-VQE would be really helpful for many applications, material science, drug discovery, climate change, and machine learning. So soon we will document Open-VQE, and you will see very nice application. One of my colleagues also, he has done the quantum battery application. So he has used the tools, and it's creativity by itself because they learn how to use the tools in order to create an algorithm. And that's the main advantage of Open-VQE, that reduce the gaps of talents. And one of them is mathematician, but now I would say is chemist because they learn how to move from mathematics to chemistry through this package. So I would really encourage for people who want to join, just contact us, and you are welcome to contribute, and whatever could be for publication, we are welcome. So in order to contact me and you wanted to contribute, you just have to follow me on LinkedIn and follow us also, and you are very welcome. Thank you very much. And now I will come back to Nathan.
Yes, thank you, Mohammed, for this very interesting presentation about UCC and Adapt-VQE. Now, as you introduced, we will delve deeper into the Open-VQE package, and I will let Hubin present it.
Yeah, sorry, just 1 minute. For those who wanted to collaborate with me in the future, please contact me. We have many things we can publish. And second, very important to know that questions can be also asked. But I think because we don't have a lot of time, you can ask me. Nathan, please write my email on the chat so people you can ask me questions. And also, OpenVQE, you can also reach it out to me through also LinkedIn or my email. Thank you. Good luck, Hubin.
Thank you.
Good luck, Hubin.
Thank you. So hello everyone. I hope I share my screen and everyone can see it. So my name is Hui Bing Chen, and following my Mohammed talk, I am pleased to give a presentation about the tutorial session of OpenVQE package. And firstly, I hope everyone might have time to clone my repo that I recently allowed on my linking post. However, I already attached it on the chat, so you can find it. So basically, it includes almost all the information about my presentation and the hand-on tutorial. First, I will start with, so what is OpenVQE? As you might have noted, it is an open source package and it provides the tool which is focused and developed for the chemically inspired adaptive method derived from the unitary couple cluster. So it helps us to facilitate the development and the testing of VQE algorithm, and is able to use the Atos Quantum Learning Machine, QLM, which is a general quantum program framework, help us to enable to write, to optimize, and to simulate quantum computing program. And secondly, why is the OpenVQE? So with the combine of OpenVQE and my QLM Fermion libraries, it helps us to implement, to test, and to develop the variational quantum algorithm, while it also offer an access to a large molecule, such as we can know about the knowledge Schrödinger style dense simulator, which can reach up to 41 qubits for any kind of circuit. So right now, you can find the paper of the package where we have some intensive benchmark, and also that helps us to provide the molecule for associated qubit count ranging from 4 to 24. So we mostly focusing on the chemical accuracy, reduce the number of circuit gates, and optimize parameter operator between a fixed length UCC ansatz and also an Adapt-VQE ansatz that Mohammed has been presented. And about this introduction, here's the introduction about the interpretability of the open source package with my QLM library, and is provided by the BIDER. So you can go to the website as the following here, and you can see that thanks to the interoperability with the quantum circuit, it will help us to translate quantum circuits from Qiskit to my QLN or vice versa through the function as the following. And also, we are managed to be using the Qiskit QPU runtime within any MyQN by using the runtime QPU class. Also, one of the most interesting thing in the MyQNL is that you can go to the demo, and they have so many demo that you can run on to test on about their system. Okay, so let me go to the next part. Here, if you can see, now we're moving to the flowchart of the OpenVQE package. And let me show you the gist repo of the OpenVQE. which is attached in the following. Yes. Here is the gist response of the OpenVQE package. So as you can see, the OpenVQE package is consist of the two main modules that are in the OpenVQE folder. You can see in here. So the first one is the UCC family, and will give the information about different classes and the function in order to generate the harmonic cluster operator. Is the code to show you very fast. And also you can draw it from the harmonic pool and the qubit pool, and in order to get the VQE optimized energy in the case of the active and non-active orbital selection. And secondly, if you go to the Adapt folder, let me show you the scheme. Go to the Adapt folder. It includes two sub-modules, which is the harmonic Adapt-VQE and qubit Adapt-VQE. So for the harmonic Adapt-VQE is containing the function that perform the harmonic Adapt-VQE algorithm step also in the active or non-active selection. And about the qubit adaptive VQE is the same. It contains the function that perform the qubit adaptive VQE algorithm step by step in the case of active and non-active space selection. And additionally, we have a folder called common 5. And in this folder is just simply they store all the internal functions that need to be imported in order to execute the two modules that I already introduced. So and also for the one who's curious, you can go to the notebook of the OpenVQE in order to test it. Which is allow you guys as the user to run and to test about the two module. So now let's not waiting anymore. Let's go to the tutorial. And what I can suggest is that you guys can set up a Conda environment, and now for the audience, you can clone my gist respo. That's what I've been attached on the group chat. And let's start now with the tutorial. So let me show first my gist respo. Here I prepare about the responses for this presentation. And you can see that firstly is just the beginning of how you install the OpenVQE package, and also how you clone this respo to make a hand-on about the experience. And secondly, there are three main extensions of the extension Python 5. The first is called the molecule UCC computation. What it do is help us to initialize the chosen molecule library and to construct the UCC standard quantum circuit, and this transform the Hamiltonian, the cluster operator, to the qubit representation. Why is this? Because our goal is to implement the Hamiltonian on a qubit-based quantum simulator. So for example, the specific harmonic Hamiltonian, it has to be transformed into a spin Hamiltonian. So like originally, you have the qubit in comparison of a spin 1/2 object. So for that reason, the only operator that can be directly measured on the quantum processing unit as a spin operator. And secondly, I call the HEA view model.py is a library for different extension of hardware efficiency ansatz. And I also mentioned about the reference, in which I consider as the second group of the ansatz is called the hardware efficiency ansatz. So what is this ansatz do? Is in fact is containing the sequence of the parameterized ansatz in single and two qubit gate, and it can be easily implemented on the quantum computer without even considering the physics of molecule property. So in my notebook, I will test it with a transverse Ising model. And the last one is about the optimization ut.py. And here I'm using the parameter shift rule for the gradient-based optimizer. So the mainly about this folder is to store the energy, the fidelity, and it's also compute the engine value of the Hamiltonian. And the gradient for this optimization techniques is in order to reduce the number of the iteration step in the VQE, and it's also help you to arrive to faster converged energy. So let's not make you guys wait anymore, and we move to the tutorial part. So first, we have to come up with the idea of how we define the Hamiltonian. And in this case, our Hamiltonian that I choose for the first phase is the quantum physics. I'm mostly focused on the Ising model, transverse Ising model. So in this part, the Hamiltonian of the fully connected transverse Ising, we define by the coefficient AI and Jij are sampled like randomly from uniform distribution from 0 and 1. And in this part, is generate a random Ising based on the number of the qubit n. And with the transverse field term of involving the X operator and also the ZZ operator, the polyterm. And in here I chosen the qubit n equal to 3. So let's just go into the detailed part of now you have to know how you construct the ansatz. So in this case, I use the library called the hardware efficiency ansatz that I already been introduced, which is the composition of the linear slide of the rotational gate and the entangling gate. So it's returned to the search function in my QLM, and also in the last part is the function count, which would help us to count the number of the entangling gate. In our case, the C0 gate and the rotational gate. So let us go into the detail of how I create the hardware efficiency ansatz in this here. So I will not go into the detailed mathematical expression, but it is simply that you have the pre-rotation that will be applied to each of the qubit containing the rotational gate Ry gates, for example, and is following by the entanglement layer. And these qubits are fully entangled and using non-parameterized C0 gate. And the last part, when you apply, is the post-rotational gate, Rz and Ry, which is added to all apply to the qubit gate. And here I call it the double hardware efficiency ansatz. You can see its representation in here, but I will change different color to the line. This is how it works, and it's how it's presenting in my QLN representation of the circuit. Okay, let's come back to the dark mode. So now, so far, what I've been done is I have defined the Hamiltonian in the spin representation, which is the transverse Ising model for n equal to 3. So, so also I have been construct the hardware efficiency ansatz as a parameterized circuit for three circuit, and I put the layer equal to 4, and I try to generate it. So in the next part, you can see that what we have done in the slide is move to the variational quantum engine solver part. What we have done is the first part and the second part where we define the Hamiltonian and we prepare the variational ansatz. And what is the next step I want to show is the stack of the open VQE, how the VQE algorithm work, which I believe that Mohammed already showed you, but I can present one more time how it work very schematically. So here you already have defined the initial guess, and the process might start with the variational parameter theta, and these parameters are the part of the quantum circuit in the VQE algorithm. We will use the quantum processor unit, which is already integrated on the MyQLM language. And the quantum processor here, what it do is responsible for the preparing the quantum state. And here is the state presentation. And after preparing the state, the energy will be evaluated as is explained in here from C theta, Hamiltonian, and C theta, where H is the Hamiltonian that we already defined as the transverse Ising model, and E is the energy that is corresponding to the quantum state. So as he's already mentioned, we can choose with the classical processor that in order to handle this optimization step. So the energy from the QPU will be fed into the classical processor. It will do the Cobila method to conjugate the gradient of the BYFCS at the as a gradient optimizer. What it's doing is to update the parameter theta in the way that it's trying to minimize the energy. And it will do it in the iterative process. It's try to evaluating the energy, optimizing the parameter, and it's very iteratively. And when the optimization is converged, and it will fed back the final energy E theta, and it's done. And on the right hand side, you can see the graph for the qubit space and time is kind of the relation between the qubit state and the time during the time of the execution for parametric quantum circuit. Let's we come back to the notebook, and here is the stack of how how the VQE actually work on the MyQN simulator. We have to see through the mechanism of this sketch. So first you have a job generator. What it do is basically which is responsible for it to generate a job that compromise a parameter quantum circuit. We already have U theta that implement the hardware FCC and that, and also the spin representation for the Hamiltonian, which is represent as the sum of the polyterm. In our case, term for the X and Z polyterm for the Eigen model. And we have different kinds of the plugin that have us to carry out the VQE method in MyQLM. Plugin is take in the generated job, the circuit and the observable, and is sent to the quantum processing units for the execution. Now we will move detail into the code part. It's very easy. It's very coherently to the schematic that I show you right after it. And first, you just need have to import the library which is needed, like the get default QPU. Very straightforward. Is have us to retrieve the default quantum processing unit to run the quantum circuit. And secondly, you have the skipping minimize plugin. This is a plugin for use classical optimization from CPy in order to minimize energy, and other libraries that I will show after. And so first you already define the job that I be present, that a job that have Hamiltonian as an observable. The model in here is a Hamiltonian, and the job type is the observable. And then you define a QPU and optimization method. Here the QPU that you define and the optimization method, and you send it to the optimizer. So in the end, the optimization method are set to different kind of optimizer, and they are the try to minimize the energy. And what is sent back the result is that you have the minimum energy VQE energy for the Eigen model of different optimizer. Here we have the Kobila, we have NetherMet, and we have BYFGS as a gradient-based optimizer. And in the next part, I have it sorting out for the state and the probability corresponding to the model that I've been testing. And also in the next figures, what I've been doing is make a plot for the VQE optimization to obtain the energy plot with respect to the step. It's called the optimization step. So here we also make a comparison with the exact diagonalization of the Hamiltonian. In our case, it's a transverse Eigen model, and to see how the energies will be converged. So in the next part, what I want to do is I made a research detail more into the gradient-based optimizer method for optimization problem. So the next one I will show you is about the parameter shift rule quantum system, which is help us to estimate the gradient of the optimization technique in order to reduce the number of iteration steps in the VQE algorithm, and also it helps us to arrive to a faster and converged energy. I will here's the detail of the mathematical in the representation for kind some kind of the optimizer. You can check it on my GitHub. And also, I will not go into really the detailed mathematical explanation, but simply it's just due to the structure of the conventional parameters like circuit gate. So the evaluated function, which are typically will be the Fourier series of the input parameter. So in this work, we use the fact that we want to derive new general parameter shift rule for single parameter gate, and we will provide an expression to compute them with a shift of phi over 2 and minus phi over 2. Here I present. Here's the gradient. The gradient is simply expressed as a linear combination of the quantum function at a shift rule with respect to the pi over 2 and minus pi over 2. And this is how I define this function. Let's go into the detail in here. I already showed you about the optimization .ut in the get optimization function and how does it look like. Let me show it in the slide. So you can see that in this function, it simply takes several parameters. The circ is simply what is a quantum circuit that needs to be optimized. In our case, the hardware facility ansat, and the QPU with the quantum processing unit that will run the circuit, and the H dash SP. So it's just an observable. Here's the Hamiltonian, and in our case, the transversing model that we will use to minimize. So the method is the optimization method that will be used. And also the number of the qubits. The size 0 is the initial wave function for the optimization. The energy is a list to store the computed energy for each optimization method. And the fidelity list is a list to store the computed fidelity, also for kind of the optimization method. So how it works is, firstly, I try to do the to go into detail. I try to do the binding variable. So this light binding variable is just binding the variational parameter x into the quantum circuit. How it's done is we sort the current variable of the circuit by using the user.get variable and binding them with the value from the x, and then it's submitted to the job QPU and the quantum circuit with the bound parameter, and it's also submitted to the QPU for the execution, and also the observable SSP, which is our Ising model, which will pass through the job, and this step will help us to evaluate the energy of the quantum state. And in the end, the energy which is equal to rest 0 dot value, and I store it in the energy list, append it as an energy. So the energy value are append to the energy list under the given optimization parameter. You can see is here the rest in here. And also, after obtaining the quantum energy and the quantum state, which is again submitted to the QPU to get the detail of the quantum state, and the psi is the quantum state amplitude that extracted from the result.rest and the fidelity. And in the end, you have the energy, which is corresponding a given set of the parameter is returned, which will be used for the optimization algorithm in order to update the parameter. So what is the goal of this function? This function is in order to evaluate the quantum circuit performance with respect to the current set of the parameter x. Here you will return two main return is the energy of the quantum state and the fidelity of the quantum state with respect to the initial state. And secondly, in this Python extension, you have the I define the gradient-based minimization strategy, parameter shift rule PMRS. Also, you have the circ, the QPU, the SSP, the observable of the Hamiltonian. So first you compute the gradient. You send it to a job with respect to the quantum circuit variable, and it's create an empty list graph in order to store the gradient value. And second is go through the loop of the circuit variable, and here is the var name in the sorted circ dot get variable, and basically this code will loop all over the variable of the quantum circuit, and it sorts the variable and restrict to the corresponding gradient, and it's sent to the job, and it will compute the gradient for each variable. And so for each variable, you can see in here, the circuit is rebound to the new parameter x, and there is a job created to submit to the QPU to evaluate the energy and the quantum state under the current set of the parameters job. And the energy are also retrieved, and the gradient is calculated by adding 0.5 times the rest value, which is the theta pi, the e theta pi plus 2 and e theta minus pi over 2 for each type of the job, in order to approximate the gradient using the finite difference. And in the end, the gradient are sorted in the gradient list. And let's move to the tutorial to see the performance. Here, the code is exactly what has been done that I explained in my presentation. And in the end, you can clearly see that I make a plot between the optimization and for the this graph for the VQE for free gradient based optimization, or with the gradient based optimization. Here for the free gradient based optimization, I use the Cobila, and the other two is the conjugated gradient, and the BYFCF is the gradient based method. So for example, you can see the first down part of the graph is the converged energy, which is measured with respect to the number of the iteration steps. And for the non-gradient based method, which is the Cobila, it took more than 200 steps. Why with the gradient based method? For example, for the BYFCS is the main concentration, it took only less than 30 steps for energy to be converged. And on the upper part, you can see the fidelity also, go up to 1 with respect to the number of optimization steps, of course. So here I move to the second phase with the quantum chemistry. I believe Muhammad have been explained you about the schematic graph for this part of how the workflow of the MyQLM. He mainly go focus on the first of the top row, which is the step for preparation of the quantum job, such containing the parameterized circuit. But however, in my part, I will mainly focus in the second row of this figure, which is the part that can be that you can, how to say, basically you can customize by the user. So here in the top row, you basically have already see that we already prepared for the step 1 and step 2, and it prepared the variational quantum circuit job that containing a parameterized circuit and the Hamiltonian. And the next step is, in the case of quantum chemistry, the circuit will be the unitary circuit, and the defined Hamiltonian will be decided for the molecule that we want to test on, and it has to be present in the spin representation. And in this stack on the bottom, so as I say, it can be customized by the user depending on what kind of the QPU they want to use to execute his job. So we can see that as it's the core, there is a minimal stack that includes the QPU, which can execute the simple job with a native quantum circuit. And we have the basic observer have been executed. For a more complex job, for example, in here, you can add additional plugin that can be added on the top of the QPU, and each plugin will responsible for a specific function. For example, you have the compilation plugin, which can adjust the circuit to fit a specific gate set, or you can modify it to ensure it can work with available connectivity. So here, in my case, in this function of molecule UCC computation, I will show you how it works in first part. Like, you can have the function that define as the get parameter. In here, you simply define the number of the molecule you want to working on, and also the geometry the charge, the spin representation, the basic sets. Here, for example, for lithium hydride, we use the most minimal basic set, which is S303G basic set, and it's return us to 22 qubit. And in the next slide, so this kind of code will define it to a function like co-compute circuit and Hamiltonian, which is responsible for the quantum circuit of the Hamiltonian for a given molecule. Firstly, is just do the PYFCF, perform the quantum chemistry computation, and this function will return back to the geometry, the basic set, the spin, charge as an input, and it will compute the integral for the molecule, such as one body integral, two body integral, and other nuclear repulsion, for example. And then it's try to convert the integral to a fermionic Hamiltonian. So the kind of the integral is that the next step is we'll get the cluster operator for the UCC and that, and this operator for the UCC and that are obtaining by the get cluster OPS with the initial guess function. And this step is very important, that which help to define the quantum operation and help us to build the quantum circuit. And these operator are normally will be paired with the Hartree-Fock approximation for the optimization process. And then you will transform it with the transform to JW Hamiltonian is we use Jordan-Wigner transformation to the qubit representation. So after construct the UCC and also you have the define Hamiltonian. Basically, this function, what is returned is the representation of the computed Hamiltonian, the quantum circuit, the number of the qubit, and the initial variational parameter theta 0 that you put on the circuit. Okay. Here, as you see, is the presentation of the Hamiltonian, and this is on the hydrogen molecule. And here's how the circuit been displayed in the MyQL representation, but I will change to the theme of Y. You see it clearly. Okay. See in the dark mode. And I make the plot. I do also the minimization for all kind of the optimization process, and I try to obtain the energy with respect to the fidelity. And you clearly can see that the number of the optimization step for the gradient-based method applied parameter shift rule have been reduced a lot for BYFCBET compared to the Kobila method. And also with this respect to the gradient-based method, we also reach to better chemical accuracy when I make it plot with the log scale of the optimization step. Okay, so that's quite a great milestone of the parameter shift rule. Okay, and in the fifth part, I was introduced about the fermionic Adapt-VQE. I believe that Mohammad already told you how dice work. So here's the detail of how it works in terms of mathematical expression, and you can also file it on my GStress board how I make it in here. And also here's a stack of the Adapt-VQE, how it works in terms of the MyQLN language, what we stack the plugin onto the slot generator in order to generate the final result. And this is the code to do the Adapt-VQE algorithm. So basically, it's an kind of an extract code what I received from the OpenVQE, and in the end, this is tested on the non-active case. Let me open it with the text editor. So it's tested on the non-active case of the H2 molecule in 631 basic sets using spin complement GSD, and it's used the Jordan-Wigner transformation, JW, which for Jordan-Wigner. So it gives all kinds of information, but what we really need is to see how many iteration steps that it needs. And in our case, only take 5 iterations, and the energy is converged at minus 1.15, for example, and it's returned back all kind of energy for each kind of iteration step to the end. We care about the final iteration step, and we make the subtract with the full configuration energy FCI, and we arrive at the chemical accuracy of order of -0.9. We have the norm of the gradient. We have the max gradient has been computed. We also compute the fidelity and the number of C0 gate, Hadamard gate, rotational gate, Rx and Ry, with so many information. And in the end, I finally make a plot for all kind of the information to compare. But I will leave that in here for you guys to explore more about the OpenVQE. But it's really interesting when we get to the arrow energy of in the log scale of 10 to minus 9, and you can test it on. And to be in more detail, I also provide the table which is extract from the paper of open source Variational Quantum Eigen solver from Muhammad, and it's very detailed. Have more detail about the method. Here we have UCCSD, UCCGSD, and Fermionic Adapt-VQE to see the computational time it takes. And that is for my part. And also for my last slide of the presentation, here are the state of the art of the OpenVQE. I will let Muhammad to take care about this part to see about the impact project, what we can do through OpenVQE. Thank you for your listening. Okay, I part.
Thank you, Hubin, for this wonderful presentation of the OpenVQE package. We can now go to the question and answer part. So if you have any question, do not hesitate to unmute your mic and ask.
So double excitations, it's the process of doing excitations.
Can you mute the micro from François?
Yeah, you hear me now?
Yeah.
I don't know if you are hearing me.
Yes, Mohammed, we can hear you. Go ahead.
Hello?
Yes, I can hear you. Yes, unmute the
Yeah.
participant.
So, I mean, very simply, double excitations is the way how you are exciting two electrons in your molecular system from one level into another level. So you are doing them simultaneously. You are exciting them. You are creating them. You are annihilating them from a state. Then you are recreating them into another state. So this is the way how can we describe double excitations. The same way for triple excitation, you have three electrons and you want to jump them, excite them from one state to another's. So let's say you have four electrons, let's say lithium hydride, for example. In lithium hydride, you have four electrons and you have 12 spin orbitals, right? In the STO3G basis set. So if you say double excitation, so you can excite two electrons, one spin up and one spin down, let's say, and you can excite both of them into the orbital of 11 and 12, for example. This is double excitation. You are exciting them from the 0 and 1 orbitals into 11 and 12. So they are described in the second quantization formalism as C dagger, C dagger, CC. C dagger is the creation and C is the annihilation operator. Thank you. Any other questions? Yeah, I have seen someone is saying there was an open QAOA package which is now stagnant. How would you keep OpenVQE going? I love this question, actually. I think I was thinking about that also in the past because also I haven't seen a lot of progress. I agree with Nathan that there has been a latest version since 6 months ago. But I would feel like VQE, it's more it's more usable now from QAOA first. You can use it in chemistry, you can use it in physics, you can use it in applications like drug discovery, like optimization problems, like material science. But QAOA for me, it's more into optimization problem. We can use it. And sometimes it can be used for simulations, but I haven't seen even recent progress on QAOA a lot since a long time in terms of research. Even though I have seen it, it can be used very potentially in industries for optimization. But I wonder why they don't really enlarge it. Like OpenVQE, we are now enlarge it very well. I think they are missing community, they are missing conferences, they are missing calls. So that would be the main reason. But I would love to make collaboration with them in the future. So I will reach them soon to see if they would be happy to have a collaboration in terms of OpenVQE and OpenQAOA. So both algorithms are potential, but I'm seeing VQE is more and more growing. So I would be happy also to see QAOA research also growing. And that's the answer I wanted to say. Thanks.
Okay, so we have a second question from François Gervais. I don't know if I say it well. In the case of double excitation, is the total energy of the system still Hamiltonian?
I actually don't understand the question very well. What do you mean by Hamiltonian? Because in VQE, the term Hamiltonian is our observable we are going to measure in order to compute the energy at the end, right? So I think if I am not wrong, double excitations are used in the wave functions. They are representing the fermionic type of your wave function, like we showed you in unitary coupled cluster. We are applying single, double, triple, quadruple. All these we are applying them on top of the Hartree-Fock state. So this is the way how we are representing them. Total energy will be computed once we put two things. The job is the wave function and the Hamiltonian. Once we do them, we compute the total energy, and that's the way how you figure it out. However, the Hamiltonian can contain single and double. So single electrons and double, single one body integral and two body integral. This is what we say. We don't call them double excitations. So I think this is the way how can I declare it for you, if I understood well. Can you explain ansatz and what are the use cases of ansatz? Of course, ansatz is a term that can represent a quantum circuit, and the quantum circuit is decomposed of number of qubits and number of gates. So whatever you are representing the system, sometimes you call them chemically inspired ansatz, sometimes we call them hardware efficient ansatz. So if you want to play with your gates without any chemistry or physics problem you are trying to figure out, then this is called hardware efficient. And if you are using unitary coupled cluster, then you are imposing symmetry on it. And this is the way we can note symmetric ansatz, for example, something like that. And the use cases of ansatz, there are a lot. I mean, if it depends on what system you want, it depends on what problem you are going to figure it out. So I would give you an example. If you wanted to work in quantum battery, for example, or in material science, then you need to compute the minimum energy of a certain system. That's why in our OpenVQE package, we provide tools that is allowing you to use OpenVQE into using VQE algorithm. On top of that, integrating it with the UCC method in order to compute the energy. And in this way, we are able to one day using the VQE in terms of for solving large molecular systems that could be important to understand and analyze the binding energies in the molecules, and that would help us to figure out the material science problem we are doing. I mean, because we are computing the minimum energy precisely. The same thing in drug discovery. If you are able to find binding interaction energies between ligands and the proteins, you could use, for example, VQE in order to help you to use active space selections in large molecules. And then you map your fermionic into qubits, and then you can solve your problem. And then you are understanding how much contact interaction between the ligand and the protein you have in your system. And then you are able to find the best interactions between the ligands and the proteins. And then you are able to find the most effective candidates for your problem you are solving in healthcare. You would suggest to OpenVQE join it in unitary hackathon this coming year. That's amazing, dear David. I mean, do you have the website? How can... Thank you, Jean-Francois, for your questions. Really very interesting. And don't hesitate to reach me out if you wanted to ask me any questions. I would be really happy to talk to you. David, yeah, I mean, OpenVQE unitary hackathon, right? Is what you mean. Why not? I mean, if it's possible, we can join them and we can check that out, and we will see, because we are able to release now with our community a lot of quizzes and a lot of hackathons using OpenVQE. So that would be a good fit, I think. Yeah. Thank you. Thank you, Nathan, for the website.
Anyone has another question?
So maybe we can wait for 2 or 3 seconds. What I wanted to say, in fact, I was really happy to have everyone have been hearing us. All of you are really valuable for us. And if you would like to be, because we have now 30 participants now live, all of you are welcome to join OpenVQE. So we are 30. We could be using you as users in the package. And those who want to be in the community, you can be contributors as well. So you are very welcome to reach out to Hubin Tran. He's an amazing guy. I like him very much in terms of OpenVQE. He's really doing a lot of jobs. Nathan also is really leading the way how we organize the OpenVQE. So we have very nice people in the package. They are able to help you. Don't be shy. Just be really passionate about the problem, and you can tell me, I would like to work in material science problem. We can work together. Drug discovery problem, we can work together. I mean, in terms of open source, I mean, and then we can help each other in order to grow together, in order to make a really nice, impactful future education in terms of quantum technology and AI in the future. So you are really welcome. And also, I wanted to tell you that I want to celebrate that I reached 25,000 followers on LinkedIn today, and this is a big celebration through our introduction of OpenVQE with the Quantum Computing Washington, D.C. and the Toronto Quantum Computing Meetup. This is really amazing, and I'm really happy for that. And we hope together in the future to discuss and to talk and to whatever can make OpenVQE better and better in hackathons, in competitions, and all together you are welcome. And thank you very much for listening to our talk. Thank you, Hubin, for the hands-on project, and I totally appreciate your work. And I hope also in the future, Hubin, you will be one of the main contributors in the package as a main sponsor for it, and someone who really can have a talk with it whenever you want, because he's really amazing guy. He knows how to organize things. He knows how to document. He's really superb. And I'm really very happy from his work. He has a lot of energy he's doing, and I really like it. In terms of Nathan also, he also has a lot of passion about quantum. And Nathan is someone who really you can rely on, because he's able to understands the problem technically. If you have a problem, he is able to switch very quickly. He's able to solve the problem. He can give you solutions. He even can tell you, wait for me 2 seconds, 3 seconds, we can go for a talk, we can go for a call. So he's someone very passionate, also very energetic, and this is what we need in OpenVQE. We need people like that, because OpenVQE is energy for me and a power in the future. So we need people like you guys to really grow the community further. And again and again and again, reach me out, please, for the package. Thanks.
You have a message in the group. Thank you.
Yeah, thank you.
Maja.
Dr. Helen, would you like to add a few words on top of that?
Thank you for your participation. It's a pleasure to host this event for your group.
Thank you, Dr. Helen. Our pleasure. And we would be very happy if you can share us the YouTube session, because we would really be happy to share it to other audiences who haven't had the opportunity to reach out today because they are busy or something. So we can share it to them later. Do you think we can do that?
Yes, the YouTube live stream is on right now, and I can trim the first rehearsal part later after 20 hours.
Okay. Thank you a lot.
Welcome.
And
Yeah, just one question. Will you have access to the whole stream on YouTube after the presentation, even the question answer part?
Yes, it's being live streamed and it's being recorded.
Okay, perfect. Thank you.
Thank you.
thank you, Dr. Helen. Thank you, Yubin. Thank you, Nathan.
Everyone.
Have a nice weekend. Happy New Year, everyone.
See you.
Have a nice weekend.
Bye.
Bye-bye.
Bye.